Swayam Prabha. Digital India. Educated India.
Hello, welcome to NPTEL NOC, an introductory course on Point-Set-Topology, Module 54, Groups of Homeomorphisms. Remember, this is a part of our study of compact open topology. So, for the rest of this talk, we will always assume that X is a locally compact Hausdorff topological space, though we may not mention it again and again. And Hx denotes the group of all homeomorphisms of X, self-homeomorphisms. That CO denotes the compact open topology on Hx. We discussed the problem whether this Hx with the compact open topology is a topological group or not. It is shown that this is not so in general. In general means just under this hypothesis, namely X is locally compact Hausdorff. It is also shown that under the additional hypothesis that X is locally connected. The answer is yes. An example to illustrate that local connectivity is not is necessary is included. That is not the correct thing. Local connectivity is necessary is included. The motivation for this discussion is that a positive answer to this problem has applications in bundle theory. We are unable to locate any discussion on this topic in the existing literature. Main question is the following: does the set Hx of all homeomorphisms of a topological space X form a topological group under the compact open topology with the usual composition law of functions? Whenever you take self-homeomorphisms or self-automorphisms of any kind, the group law is always the composition law. Of course, it is natural to demand that X is locally compact Hausdorff space because we are dealing with compact open topology. It seems that all working mathematicians who have to use this result assume the truth of it. I too have been assuming this, though I have not used it in any of my research works. The point is that the statement is true for a large class of spaces which are interesting to topologists. For instance, if X is compact, we will see an easy proof of the assertion here. X is discrete, you can do it by hand and see that this is also okay. X is a manifold, not easy. X is locally finite CW complex, that is not easy. So these are the things, some sort of proofs seems to be there in the literature, but nobody has written down anything. So whenever people have used it for, especially for manifolds, apparently they are sure of that the result is true somewhere. So that is the whole situation. We first notice that the proof of an affirmative answer to the above question in the case when X is compact is quite easy. So naturally our first attempt to prove the same for a non-compact locally compact Hausdorff space is to go to the one point compactification do use the theorem there and try to bring back, try to come back. Note that every element f belonging to Hx has a unique extension f hat, which is also a homeomorphism, such that the extra point f hat of star is just the star, that point at infinity, whatever you want to call. X star is the one point compactification here. Also note that the association f going to f hat can be used to identify the group Hx with a subgroup of Hx star, namely those which fix the point at infinity. Therefore, we are led to ask the following question: does the compact open topology on Hx coincide with the subspace topology from Hx star? Start with Hx star, give the compact open topology. You can take the subspace topology, because this is a subset now. You can treat this as a subset, actually subgroup. But the question is whether that subspace topology is compact open topology in its own right on X, on Hx. So it turns out that this question seems to be harder than the original question. Indeed, one can more or less see that the two questions are equivalent. At least this is harder in the sense, it is stronger in the sense, you can, if this is true, then you can get an easy proof of question number, this question, main question. So the answer to our main question itself is not always in the affirmative. The example that we have is obtained by removing origin from the standard deleted middle one-third Cantor set in the unit closed interval. On the positive side, we have the following result. Let X be a locally compact, locally connected Hausdorff space, and Hx denote the set of all homeomorphisms of X, self-homeomorphisms. Okay. Take the compact open topology on Hx. Then this Hx-CO is a topological group. On the way to prove this theorem, we shall see that the result holds for all compact Hausdorff spaces without the extra assumption of local connectivity. So we don't have to prove that one separately. Okay. So let us start proving, but there will be many interruptions in between. So let us hope we can start proving. Recall that the compact open topology is generated by subbasic open sets of the form this angle bracket KU, such that all f belonging to Hx, such that Fk is contained inside U. Remember, this notation we used for all continuous functions when we were dealing with space of all continuous functions. Here I have restricted myself to only homeomorphisms of X to X. Therefore, the same notation I will use. The notation is changing, so that's why I have carefully rewritten it here. Now this is actually the old notation Ku intersection with Hx. That means only the homeomorphisms are taken, not just all continuous functions. So that is what you have to pay attention to, that one. In any case, inside Hx is a subspace of all continuous functions from X to X, right? So this is subspace topology there. Therefore, if you take these the subbasic open sets in the bigger topology and intersect them with the subspace in the subset, they will be subbasic open subsets for the subbase topology. So there is no problem in that one. So this is the subspace topology from the compact open topology on all continuous functions. For a locally compact Hausdorff space, by B of our earlier theorem, namely exponential correspondence theorem, the continuity of the composition map hx cross hx to hx for f comma g to f composite g is a consequence of the continuity of the corresponding function under evaluation map and so on, right? You have to evaluate it at x, hx cross x, and evaluate it fg operative upon x, fg of gx. This is a function, this evaluation function is a map into x. So if this is continuous, then that is continuous. This could be any domain, okay, in some domain into the space of continuous functions in a function space is continuous if and only if composite with the evaluation map here is continuous. That is what we have seen in this is the theorem we have used it several times. Now we are going to use that also. Okay, so how to verify that this f comma g comma x going to f composite g of x is continuous on this product space hx cross x I have to take to hx. All right. So to verify this, namely this one, fix f, g and x such that this composition and operated on x is inside an open subset U. Okay. Then I have to produce a neighborhood of f cross a neighborhood of g cross a neighborhood of x such that under this function the entire neighborhood goes inside U. So that is the continuity at this point. So start choosing an open subset V such that gx is inside V and V bar is compact and f of V bar is contained inside U. So this I am doing by the continuity of f. F of gx goes inside U. So some open subset goes inside U under f. That open subset V can be chosen to be compact also. And so closure is compact also because the local compactness. Similarly, once you have chosen this V, now f of x goes into V, right? Therefore, you will get an open subset W such that x is inside W, W bar compact, G of W bar is inside V. Now it is straightforward verification to see that V bar cross U, so this V bar is compact, this is open, right? So all function, all homeomorphisms taking V bar into U, that's a neighborhood. Neighborhood of what? Neighborhood of f, because f is one of them. So this is an open subset. This is an open subset. This open subset contains G, and this is the open subset started with chosen. So it's a W, so it's x is inside W, right? So this is an open subset of f comma g comma x. This is an open neighborhood. Okay. So if you take, you take arbitrary, say f prime, g prime, w prime with this property, the composition will land up inside W is very straightforward to establish. Okay. So in particular, it follows that once we have proved that the composition is continuous, you can restrict it to fix f, look at G going to f composite G. So that is a left multiplication by f. Fix G, so fix f, okay, sorry, fix G now, f going to G, f composite G, that is a right multiplication by G. So both of them will be continuous, that's all. So this is a standard thing. So left, which is left multiplication by f, RF is a right multiplication by f. So both of them are continuous. Okay, from hx to hx. The main thing here is to prove that the inverse is also continuous. Once you prove that, it follows that the group laws are continuous. Therefore, the hx is a topological group. So this is what we have to prove. Here is an elementary result that we want to use. Since this doesn't seem to be very common, let me just take a few minutes to state it clearly and then prove it also. In general result, let G be a topological space with a group operation G cross G to G, continuous, only assumption is the multiplication is continuous. Suppose further this eta from G to G given by G eta G is G inverse, that is the inversion map. Okay. Suppose this is continuous at just at A. Okay, just at any one point, so better take at A. Then eta is continuous on the whole of G. This kind of results we must have used in any topological group itself. Like if you have a continuous homomorphism, any homomorphism which is continuous at identity E comma E will be automatically identity on the whole space, on the whole group, and so on. Differentiable functions, if they are group homomorphisms, differentiability at a single point, then it will imply differentiability everywhere, that kind of thing. But in all of them, you already have a topological group. Here, the kind of result that we are, a technique that we are using is the same, but only continuous function is, only multiplication is continuous. The eta G is not yet continuous, that you can't assume. We are going to prove that this inversion eta is continuous now. Okay, so that is why this is not all that common. So let me tell you the proof. We first note that for each G inside G, the left multiplication, right multiplication are continuous because the multiplication itself is continuous. Since LF inverse, okay, is equal to L of F inverse, and RF inverse is R of F inverse, it follows that LF and RF, each of them is a homeomorphism. Okay, first of all, they are continuous. But same reason, L of F inverse will also continuous because F inverse is another element there. Okay. So now let F belong to G be any element. We want to check the continuity of eta at that point. Okay. So first you check the following thing. The inversion composite LF is nothing but RF inverse of inversion as a map from G to G, as a function from G to G. So this is the commutativity law. Eta composite LF, when comes it on this side, it will be RF inverse of LF. Okay, this is very straightforward verification. This is true in all groups. Okay, since RF inverse is also continuous on the whole of G, it follows that RF composite eta is continuous at E. Okay, this is homeomorphism. It is just a continuity of this one, implies eta is continuous at E. So when you take the composite to another continuous function, the composite will be also continuous at E. Okay. So this side now, eta composite LF, we know is continuous at E. But now LF is a homeomorphism. Therefore, it will follow that eta is continuous at LF of E. Okay. So all that you need is to use that LF is open mapping. Okay. So this will be easy. Indeed, you can, if you are familiar with taking the sequence, sequential continuity and so on, you can use that also. Only thing is, the space that you have taken, you will have to assume first countable. The alternative is there. You have learned it in this course. Namely, you don't have to assume first countability. What you do? You take nets. Show that use the convergence of nets. Okay, so that I will leave to you as an exercise. This is also just entertaining exercise. On the other hand, using nets to prove this one is like using an atom bomb to kill a sparrow. So let us use this result now, namely continuity at one point, namely at identity, is enough to prove the continuity of the whole thing. Okay, therefore, this come back to this special case now, eta inversion in Hx to Hx. Okay, I have to prove that it's continuous at the identity element of this group Hx. Okay. Also note that the inversion is a after all, by the very definition, it is a inversion. Inversion is usually inversion of inversion is a identity. Eta inverse, this involution. Okay, eta inverse is eta. So they are same. So showing that it is continuous is same thing as showing that it is open. Okay, we need to show that sets of a form eta of ku, okay, are neighborhoods of identity of x, where k is inside u, because neighborhood of identity means what? F of k must go inside if identity belongs, f of k is k itself, it must be inside, so k must be inside u. That's how we have to take. So k is compact and u is open. That is the standard thing for all subbasic open sets. So we have to show that eta of ku is the same thing as eta inverse of ku. We have to show that it's a neighborhood of identity, because these are neighborhoods of identity you start with, provided k is contained inside u, k compact and u open. Okay. So just do this elementary algebra here. F is a point of function in eta of ku, means f inverse is inside ku, right? So that means f inverse of k is going inside u. And that is the same thing as saying k goes inside fu, because f inverse is after f is a homeomorphism. If k is goes fu, because now k is f is a 1-1 mapping, okay, it's a bijection. The complement of k will contain f of the complement, but this is same thing as f of the u complement. So f of u complement is going inside k complement. It's same thing as in this notation, f belonging to this Langle uc comma kc. So starting with this an open subset, you have to show that this is an open subset. In the definition of compact open topology, such sets are not there, you see. To allow this as a subbasic open set, I need this one to be compact and this one to be open. Luckily, since k is compact, k is closed, so inverse image, the complement is open. But why UC must be compact? U is just an open subset. Okay, so that is the one of the main why this is a non-trivial problem. So we have to show that this is actually open. We don't need to show that. We have to just show that this is a neighborhood of identity. That's enough. Okay, that will be equivalent to showing that this open. Actually, eta itself will be a continuous function after that. Therefore, we need to prove that sets of the form Langle UC comma KC, where U is any open set and K is compact, K contained inside U. These are neighborhoods of identity. Of course, we need to consider only the case when K is non-empty. Okay. If K is a whole space, KC will be empty, right? So if K is empty, KC will be the whole space. So this will be automatically a whole, there is no condition on that one. So that is not a important thing. And UC is non-compact. If UC is compact, then this is again open subset, basic open subset, subbasic open subset. There is no problem. So in particular, if UC is compact means what? U was arbitrary open subset. Therefore, UC is an arbitrary closed subset. When it is compact, the space itself is compact. Once a space is compact, there is no more work to do, because this will be a compact subset, that is an open subset. These are subbasic open sets. So you are home. So that's what I say, that we have already now got a proof of the assertion that in the case of X is compact. Okay, this is on the way, but we want to go ahead without this one. So far we have not used local connectivity at all. Okay, just compact Hausdorff space is good enough. Okay, now we want to use local connectivity. Okay, so here is one more elementary lemma. Okay, so we should state and prove this separately instead of using it in the run of the proof. Let X be a locally compact, locally connected Hausdorff space. Let K contain inside U subsets of K such that K is compact and U is open. Then there exists an open subset W of X such that this W is the union of finitely many connected open sets, each of which is actually compact also. In any case, what I want is W bar is compact and K is contained inside W, contained inside W bar, contained inside U. Okay, the statement is K is compact, U is open. So in between, you can always get this one, such that W contains a W bar by regularity. But what I want is this W itself is the union of finitely many connected subsets, and each of them such that their closure is compact, so that W bar will be also compact. So that is the extra thing, and that extra thing comes from local connectivity. Okay, the rest of the statement is just regularity here. So let us go through the proof. This is not a difficult thing. For each point inside K, because that X belongs to U and U is open, and because the space is locally compact and connected, locally connected, I can choose X belonging to Vx contained inside Vx bar contained inside U such that this Vx is connected, Vx bar is compact. The first you choose such that Vx bar is compact. Inside that you can choose a local connectivity, you can choose another open set which is connected. Its closure will be contained inside the closure of the original one which is compact, so it will be compact. That is the way you can prove this one. Okay. Now, so that is what I said. This is possible because X is locally compact first and then locally connected also. Since K is compact, you can get a finite cover, K, X1, X2, Xn, all of them inside K such that K is contained inside Vxi, I ring 1 to K. I am denoting that as W. So that was the assertion. There is such a W. So this W is the union of these connected subsets. Each of Vx bar is compact, therefore W bar is the union of finitely many closed subsets V bar, so that is also compact. So all of them is contained inside U. Over. So we will use this one, and now let us continue with the proof of theorem. So let Vxi's and W etc. be as in the previous lemma, just now which we have proved. For a notational sake, I will put L1 equal to W bar. I am starting some kind of induction, not very big induction, only a number of steps here. Using the regularity of X, remember this W bar is compact and contained inside U. So I choose this L1 is W bar, L1 is contained inside U. So in between I will choose another L2 which is also compact, which is a neighborhood of this one. So L2 interior is contained inside L2, that contains L1. So similarly in between L2 and LU, again another one, we will call it L3 interior contained inside L3. Okay. So these are all compact subsets now. Okay, L2 and L3. Their interiors contain the previous one. Okay, so L1, L2, L3 contained inside U. Now you take V equal to interior of L3 minus L1. By the way, this kind of things we have done several times in proving paracompactness and so on. Okay, whenever you have Hausdorffness and locally compactness and so on, so you are using normality is here strongly regular because things are compact and so on. Local compactness is extra thing, that's all. Okay. So take this V interior of L3 minus this closed set L1. So this is an open subset, and put T equal to just the boundary of this L2. L2 is a compact set. Throw away the interior of L2. So that is the boundary of L2. So I will just denote it by T. Okay. So here is a picture what we have done so far. Started with this rectangle here K contained inside this large open set here. So in between, the first thing was to take a W such that W is union of finitely many connected open subsets such that each closure is compact. So those are the VXIs. Okay. So this W covers the whole of K and is contained inside U. That's all. After that, I have chosen the notation W bar to be L. So that's a compact set. Then I choose L2, then I choose L3. Okay. So that's all the picture. What is this V? This V is this L3 minus L1 interior. The other way around. L3 interior minus L1. So there is an open subset. So did I make V open subset here? L3 interior minus L1, right? And then T is just the boundary of L2. Okay? So I have drawn nice pictures. Pictures will not be all that nice. Okay? I have drawn a circle here and so on. This T need not be connected and all that. The only thing is this W is a finite union of connected sets. Okay, there is no other way. K is not connected, U may not be connected, nothing is. There is no connectivity assumption anywhere else. Now you take G equal to Xi, Vxi, Langle. So this is an open set. Intersect with I range 1 to K, that is an open set, basic open set. Intersect it with further with T comma V. T is compact, V is open. So this is an open set. Xi's are in Vxi's, T is inside V, therefore identity map belongs to this intersection. Okay? Therefore, this G is a neighborhood of identity in Hx. Now look at the complement of C, complement of U, this portion. Okay, this portion is contained in the complement of L2 also, because L2 is inside U, right? So complement of U is inside the complement of L2, and complement of W contains complement of K, because K contains W. K is contained in W. So I am just reversing De Morgan law, that's all. It follows that if you take L2C, WC, the angle here is contained inside UC, KC. See, WC is inside KC, so everything coming here will be inside KC also. On the other hand, this is a smaller set. L2C is a larger set. If a larger set is going inside here, the smaller set UC will be also going inside that under whatever function you take. So this Langle, all functions, all homeomorphisms from X to X which take L2C into WC is automatically contained inside this one. Okay, this is set theoretic result, property of this Langle function, that's all. Therefore, it follows, it suffices to prove, we want to prove, what we want to prove, we have to forget that one, that this G we have selected, right? Where was this here? This G, right? This is an open subset. We want to show that this is neighborhood of identity contained in this open subset, namely UC, KC. Okay. So instead of that, we can just show that this is contained inside this set here. That's a stronger statement. Okay. So let us prove that G is contained inside L2C, WC. Okay. Now consider this thing. T is a closed subset, right? So x minus t, if you think of this one, what is t? T was the boundary of L2, right? Whatever is remaining is the interior of L2 minus the complement of L2. Complement of L2 is open, interior of L2 is open, they are disjoint. The union is precisely x minus the boundary of L2. This is T. So this is a standard way of getting a separation. Okay, this is nothing very special about L2 and so on. You could have taken any compact subset, okay, and take the interior of that and the boundary of that. The boundary of that will separate the interior with the complement. That's all. For now, take any function, any homeomorphism in G. Any homeomorphism will do for this particular thing, but we are interested in what is happening for elements of G. Okay. So since f is a homeomorphism, f of this will be another separation. What is f of x? It's x. What is f of t? It is ft. So x minus ft will be equal to f of L2 interior and disjoint union with f of L2 complement. Okay, a separation goes to a separation under a homeomorphism. Okay, now look at all the xi's which are inside Vxi's, okay, and Vxi's are contained inside L2 interior, right, because they are inside L1 itself. So we have f of xi. If you take f of that, it will be inside f of L2 interior. Also, ft is contained inside V, okay. In this picture, if you remember, ft remains here, t is here, ft will remain here because f is inside G, right. F is inside G, t of f of t is inside V. That is the hypothesis used here. So ft inside G, ft inside V, and hence does not intersect any Vxi's because Vxi's are inside L2 interior, inside L1 interior. Sorry, L1 interior. So I have subtracted the entire L1 from L2, L3 interior. So that is V. So they don't intersect Vxi's at all. Okay, and hence all the Vxi's must be inside x minus ft. Okay, because ft doesn't intersect this one, so Vxi's are x minus ft. But Vxi's are connected, so this is a separation. Therefore, Vxi's must be in one of them. Okay, so Vxi is connected. On the other hand, Vxi intersection f2, f of L2 interior is non-empty because f of xi is there, right? Xi, Vxi, f is here. You see, again, x is inside this one. So xi, f of xi is inside Vxi. Xi is also in Vxi. But xi does not move out of Vxi under f. So these f of xi's are in the intersection. So Vxi intersects this one, therefore it must be completely contained inside f of L2 interior. So it cannot intersect this part, okay, being connected. Okay, this is true for all I have never used anything about xi other than anything about I here special. So the entire W, which is the union of Vxi's, is contained inside f of L2 interior. Okay, but look at this one. If something is contained inside L2 interior, its intersection with f of L2c is empty, right? Therefore, what we get is WC, the complement of W, which contains complement of this. The complement of this first part will contain this whole thing here and more perhaps. In fact, complement is being taken in X, so it will contain Ft also, doesn't matter. So it contains f of L2c. So what we have proved? F of L2c is inside WC. Okay. What does that mean? F is inside the angle L2C, angle W or angle WC. That's what we wanted to prove. L2C, WC. Started with an F element here, it is here. So that is the proof. Okay. So proof is over. Indeed, the next thing, namely producing a counterexample, that is, if at all you think this is difficult, that will be a little more difficult. Okay, so let us come to that. So before that, I will tell you the history. This history is very recent, after all, it is just about 3 years old. So whatever I remember, I have put it here already. Attempt to find a justification for locally connectedness assumption in the above theorem initially led us naturally to the topologist's sine curve. Recall that this topologist's sine curve is a subspace of R2, is a compact subspace of R2 actually, which is the union of the graph of sine pi by x on the interval open interval 0 to close interval 1, open to close it. Okay, you take sine pi by x, take the graph together with the closed interval 0 cross minus 1 plus 1 on the y axis. Okay, I am just I can't go into the full study of sine pi by x now, but I am just recalling you this was system. This is a compact set. If you take this one with the compact open topology, the homeomorphisms of this space, that will be automatically topological group because this is compact set. So what we want to do is, destroy the compactness by removing a point. So do that, namely take this very special point 0, 1. Okay, 0, 1 or 0, minus 1. These are two special points there. So remove one of them. So remove this one from this and obtain the topological space X, which is now non-compact. It is locally compact. Okay, this is subspace of R2 after all. It is Hausdorff also, and it is connected, but not locally, even locally connected. It is not locally path connected, it is not locally connected either. We can then think of the original space as the one point compactification of X. Okay, so I was trying to prove or disprove, actually I was trying to prove that in this case there is an assertion, namely affirmative answer, namely Hx is a topological group. But it turns out that understanding the structure of this, the group structure of Hx is very important, and we don't know it very well yet. So I had to abandon this example. But this leads to a sub-question here, namely this attempt is what? That is important here. Going to one point compactification, right? Forget about this particular example. Try to do it in general. Okay, so that is why we have that the sub question. Anyway, it doesn't matter now. So the point is that I wanted to say is that this attempt was not successful yet. Successfully yet, I haven't given it up yet, of course. Okay, so the next example is, you can guess what is it? The Cantor set. So Cantor set did help. Okay, so let us study the Cantor set now. So what I am going to do? Cantor set is also compact. Remember that. So I want to destroy the compactness by removing a convenient point. You can perhaps do it with any point, but most convenient is remove the point 0. Okay, So recall that Cantor set was obtained. This is 1/3 deleted middle 1/3 Cantor set, namely for each integer I, 1, 2, 3, whatever, I divided by 3n to I plus 1 divided by 3n. Okay, you keep deleting these open intervals. First you delete 1 by 3 and 2 by 3, 1 by 3 to 2 by 3, and then you 1 by 9 to 2 by 9, 4 by 9 to 5 by 9, and so on. You keep deleting them. Okay, that is a construction of the Cantor set. Okay, so if you take some open interval of this length, 1 by 3 power n, and next one 1 plus 1, k plus 1 3 power n, I by 3 power I plus 1 3 power n of this length 1 by 3 power n here. This may be empty because this is already in the deleted part. If it is not empty, inside that you will get a carbon copy of the Cantor set again. A subspace of A which is of this nature, provided it is non-empty, depending upon value, will be called a Cantor subset. It is again a carbon copy of the Cantor set. Means instead of starting with 0, 1, I could have started with this interval and then did the same procedure for that interval. That's all. So we shall use the following facts about a Cantor subset. So Cantor subset I am denoting by A. So each Cantor subset is homeomorphic to the entire Cantor set C through an affine linear map. Endpoints you take and take an affine linear map which will send the endpoints to endpoints. That's all. Automatically it will give you a homeomorphism of the Cantor sets. Each A is clopen in C, open as well as closed. Okay, if J is an open interval, non-empty open interval, and A intersection J is non-empty, then A intersection J, inside that A intersection J contains a Cantor subset. So that may be A prime or A1 or B1, whatever. Each open interval, okay, that is the property of Cantor set. It is repeated, it is copied inside every Cantor subset also. That's what I wanted to say, that's all. Finally, this may need a little more proof, similar to our lemma about local connectivity and so on, but see here this is a different kind of game. But proof is not difficult. Take any Cantor subset contained in union, finite union Li, okay, of some open finite covering by Cantor subsets. Okay, no, it's not an open covering, it is clopen covering. In Cantor subsets are clopen, you know that. It's not just open covering. Okay, the finitely many compact subsets of Li. That's enough. A is a Cantor subset. These are just any compact subsets. Okay, there may be some points also here, and so on. Some intervals also. I can take compact subsets of R to begin with. So A is contained in the union, and each Li is compact with all that. Then there exists a clopen subset B of A, which is homeomorphic to C. All that I say is B is another Cantor subset. That's all. There will be a Cantor subset of B, which is Cantor subset of A, such that the property is important. B intersection Li is non-empty, implies B is completely contained inside Li. See, there are finitely many of them. Look at L1. B intersection L1 non-empty, it must be inside that completely. If it is empty, that is fine. So some of them may not intersect. The moment they intersect, they will completely contain B. So that is the meaning of this one. Okay, this is true for all the R. So some of them contain completely, some of them may not contain. That's all. None of them may contain. That is not possible because union is inside LR. The whole thing is LR, right? If all of them are disjoint, that is not possible. Okay. So this is the assertion here. So this will be used in a very peculiar way. You will see that namely, so now I take x to be the Cantor set minus 0. We claim that the inversion map is not continuous. Okay, so it cannot be a topological group under the compact open topology. As seen before, it is enough to produce a compact subset K and an open subset U such that this eta Ku, which is UC Kc, this we have seen already, is not a neighborhood of identity. Over. If it were a neighborhood of identity, if you have tuned all the time, then you know that eta would be continuous. So one single example of this nature will show you that it is not continuous. So all that I have to choose is start with a compact subset K and an open subset containing that. Look at U complement and K complement. Show that this Langle U complement K complement. That's of course it is a it contains identity because K is contained inside U, so U complement is contained in K. The identity is there, but this is not a neighborhood of identity. No basic subbasic open intersection of subbasic open sets. No basic open set containing identity will be contained inside this one. So this is the claim. Okay. So what is the choice? I have to choose some K and something, right? One single choice such that this happens is over. So what is the choice? Our choice is K to be this 2/3 to 1 intersection C. So this is another Cantor subset. Okay. First 0 to 1/3 contains 0 which I have thrown away. This is 2/3 to 1, that part I am taking. So that is my K, which is a Klopen set. So I take that itself as U. It is compact, it is open. Okay, so I can take K equal to U. So in this one, I am shown that this Kc, UC Kc is not open. That's what I have to show, not neighborhood of identity. So for brevity, we will just put C0 equal to K complement, which is x minus K. Remember where I am taking the complement here now, in the space x. Okay. We now show that this C0, the C0 is K, K is also U. Okay. So what I have got is here C0 is not a neighborhood of identity. Okay, the statement is obvious. So far only notations and all this I have done. So now I have to prove this one. Okay, now the proof starts. Let K1, K2, Kr be any finite collection of compact subsets of X. Let Ui be open subsets containing Ki's. One more K0 you take, namely K0 equal to U0 equal to C intersection 2/3 1. Okay, you include this set also. We claim that the intersection I ranging from 1 to R, Ki Ui, this is obviously candidate. If this contains identity and this is an open subset, any open subset which contains will contain an open subset of this nature, because these are basic open subsets, and this is most general. Whenever you have chosen like this subset is not contained in C0 is what I have to show. Even if one such thing is contained in, then I am finished. I cannot, my claim is wrong. So for every Ki is chosen like this, finitely many compact sets and open subsets like this, if I want to show, don't worry about K0, why you should have taken K0 U0. I want to show that Ki Ui itself is not contained inside. Even after taking the intersection, it is not contained in. Even the smaller set is not contained in, larger set will not be contained in. So that's why I can take this extra thing also. So this is a special one I have taken, but these are general things. Okay, so that will show you that C0 is not a neighborhood of identity. So how to construct? You have to construct a special function here now, which is a homeomorphism of this x, C minus 0. which belongs to this one but not here. That's all. The idea is to construct a homeomorphism from C to C itself, shuffling suitable Cantor sets such that 0 goes to 0, so that if you throw away 0, it is still a homeomorphism of X. That's all. And this F is on the LHS here, but not on the RHS. Okay, now the construction starts. Look at these finitely many K1, K2, Kr, which are compact subsets of X. Okay, 0 is not a point of X. It is inside the Cantor set C, right? So this distance is positive. This is the usual metric, usual distance in R, nothing more than that. Okay, this distance is positive. Choose n such that 1 by 3 power n is less than d. Okay, so that 0 to 1 by 3 power n, that interval does not intersect any of these ki's. That's all. Okay, a small interval around 0 is taken. Of course, 0 will be thrown out afterwards. That interval is not intersected by none of these ki's. That is the important step here. Note that this k0, whatever we have taken, k0 is this is one of the Cantor sets, right? It is a Cantor subset. The k0 is a Cantor set. By the above remark 4, I told you k0, I take now A equal to k0 and union I into 1 to R ki. So this is not A is there, k0 union all these things. Okay. So then A is contained inside that. Okay. I apply A equal to k0. Okay. I take A equal to k0 and k0 is I into 1 to R ki. K0 is there. K1, K2, Kr may not cover k0. So I am taking k0 also. But what are they? They are compact subsets. So I can apply it to the A is taken as k0, but I apply this remark 4. There exists a Klopen subset B, okay, which is a copy of Cantor set such that this B is contained inside ki, I range 1, 2, 3 up to S, and the rest of them it does not intersect. This S may be 0, whatever, S it will not be 0 because S will have to be contained inside k0. Okay, so that is the one of the, for example, suppose ki's were all disjoint from k0. Then I can take k equal to this B equal to k0 itself over. Okay, so B is inside ki, so I have put I equal to 0 here very precisely. But 1, 2, 3 up to S, they are shuffled. The k0 is a special one. All k1, k2, k are arbitrary. You can label them whichever way you like. You don't know what. I am taking the first S of the S of them, okay, and labeling them as 1, 2, 3 up to S, S of them. What is the property of that? They all contain B. That's all. This S may be just 0 also. I don't know. This only 0 part may be there. Okay, doesn't matter. The rest of them don't intersect K at all. So choose such a thing. After, that's why after reindexing the set K1, K2, Kr. Now let us do some more bifurcation. The whole idea is the subsets of these Cantor subsets can be written, disjoint union of so many copies of themselves and so on. So that is the whole idea. This fractality of the Cantor set is used very nicely. Take C1 equal to 0 to 1/3 raised to n intersection C. Okay, so this part does not intersect none of the ki's. That's what we have chosen, this 1/3, right? This 1/3 raised to n, that has been chosen in that way. So look at that one and call it as C1. You write C1 itself as disjoint union of two Cantor subsets. Okay, you don't have to worry. Just write it as disjoint union of two Cantor subsets, because this is Cantor set. How is the next thing? How it's constructed from this interval? You remove the middle 1/3. So you get two of them. So take those intersections. So C11 and C12. You can always do that. Okay, whichever way you like, doesn't matter. Now you write Ki equal to Ki prime union with B, because these Ki's contain B. Right? What is B? B is a Cantor set. Therefore, it's a Clopin. Okay, so I can again write Ki as a disjoint union of Ki primes, which will be also Clopin. Okay, because B is Clopin and I am taking the complement here, Ki primes. But what happens to other things? Don't have to worry, because Ki's don't intersect that part. Okay, finally you have B itself is subset of K0, right? It's subset of K0, K1, Kr. So that B itself you write as B1 union B2. So all these B1, B2, B and C1, C11, C12, they are all Cantor subsets. The disjoint union of non-empty Clopin sets. Okay. Now we assume that 0 is in the closure of C11. Remember, 0 must be, I have taken the whole thing, right? So 0 is inside C11 part, you can take. So I should take open interval. So C1 it is in one of them. So it is in the part of C1. That's all I want to say. Okay, 0 is in the C11 part. Okay, note that C11, C12, B1, B2 are all Cantor sets and all are Clopin sets. That's I am repeating here. That's all. Now look at the union of all these 1, 2, 3, 4. That itself is a Clopin set inside C. So the entire C can be written as C11, C12, B1, B2, disjoint union with another L, which is also a Clopin set. All right. Now the major work is over. Now I can define the homeomorphism by merely shuffling these things. So one thing you have to notice is this L, which is a complement of all this, will contain all the complement of B inside Ki primes, and all those things which B does not intersect, namely Ki I ring from 1 to S plus 1 to R. So L will contain all of them. Okay, L will be many more other things also. All rest of the C is there. So now define F from C to C as follows. First C11, C1, both C11 is a subset of C1, right? But both of them are Cantor subsets. So take a linear homeomorphism which is order preserving, and both of them contain 0. So make 0 go to 0. You could have taken the other way around. So order preserving automatically implies that F0 is there. Okay, if I say F0 is 0, the rest of them has to be order preserving because it is homeomorphism. Okay, so let F from C12 to B2 be the order preserving linear homeomorphism again. Both of them are Cantor sets. There is a homeomorphism, all that I am assuming. So they are all disjoint. So I am totally independent in defining these homeomorphisms. So F on this one, and so on. Okay. Then F from L to L being the identity map. Last, B to B1. See, B1 is a subset now. So C1 was subset and I went on to larger set here. Now I have to cover this part. So I will take B to B1 with the order preserving linear homeomorphism. Okay. So since I have covered the entire of C, okay, because they are all disjoint things and they are going to disjoint things, the image and the domain and image are covered completely. So F is a homeomorphism, it's a continuous bijection and hence is a homeomorphism. F0 is 0, therefore if you throw away 0, F restricts a homeomorphism from X to X. Okay. Now look at 3, which is identity on this L, and 4 which says B going to B1. So these two are important. It follows that this F takes Ki to Ki. Okay. These Ki's are fine because where are they? They are inside L, so that's identity. What about these Ki's? These Ki primes are again inside L. Only the B part you have to see, right? The B part is going inside B1. So this Ki is going inside Ki. I am not claiming that F is a homeomorphism here. No. F of Ki goes into Ki for each I. Okay, and these are contained inside because Ki's are contained inside Ui. So each Ki is contained inside Ki Ui. So this intersection is contained inside. So F is here. So that was the first thing we have to see. Now finally I have to see that F is not in C0, C0. Since F sends C1, 2, which is inside B2, to all the way inside 2/3 1. Okay, remember, so this B was a subset of 2/3 1 here. So C1, 2 is somewhere away from that one, right? So it follows that F is not in C0, C0. Okay, 2/3. What is C0? Remember, C0 was the complement of, let me just show you what was C0 to begin with. This is C0. C0 is short notation for complement of K. Okay, and my K itself is 2/3 1 intersection C, right? So it has gone out of the complement, so it is not going inside C0 at all. So therefore this F does not take C0 inside C0. So the proof is over, namely Cantor set, the group of homeomorphisms, is not a topological group. So there are a couple of questions that automatically rise in this context. Namely, find a criterion for Hx under compact open topology to be a topological group, where you don't try to put anything other than X equal to locally compact ortho space. The criterion means what? Suppose this is locally compact, then X must be this. If X is something, then that is one way that I have given you, namely locally connected, locally compact Hausdorff space. Right? Equivalently, you can take one point compactification, try to solve the subspace problem. Is the subspace on Hx coming from Hx star, whether that is the induced, that is the subspace topology, whether that is compact open topology. Okay. Or you can try to solve this problem in the case of sin 1 by x and so on, interesting cases like that. So there are quite a few problems left. It's fun. Well, that is it. So I told you that these things were done a few very recently, about 3 years back. So during a conference, during a workshop in characteristic classes, in which Shamik Paul attended it, and we were sharing a room for some time, and that time I was discussing with him. Then I am thankful for Alan's, this Alan Hatcher. I asked him whether he knows. He says he doesn't know, but maybe look it here and so on. Then I asked Dennis Sullivan and so on. The most important of all, my initial attempts were discussed with Parameshwar. So he said, look here, you have to be careful and so on. Parameshwar was there. He painfully went through the initial versions with so many typos and so many misgivings there, but he saw through the whole thing and made it where I should be careful and so on, gave up some warnings. So I should thank all of them. Of course, I thank you for listening to this one also. It's a good opportunity of presenting this one. Okay, so thank you. We will meet next time.